Today we'll begin our probability unit. Probability is the mathematics of randomness, uncertainty, and risk. This is a branch of what's called pure mathematics. Statistics is the art and science of learning from data. It is a branch of applied mathematics and relies on probabilistic results. Probability and statistics is understanding the randomness in sampling and experimental designs to make inferences to and justify claims about the population. Today we'll learn about sample spaces and basic probability. Here are three classifications of probability. Subjective, which assigns probabilities to outcomes or events based on personal belief. For example, Aurelie is in Vegas playing craps, and her intuition tells her the next roll is going to be an 8. She has such a good feeling about it, like she has an 80% chance of being correct. She puts her money down on 8. The dice are thrown. It is not an 8. Her intuition in gambling is always wrong. This may or may not be based on a true story. Empirical probability involves relative frequencies of a particular outcome or event in repeated trials of a simulation. The empirical probability of rolling an 8 with 2 dice could be calculated by rolling 2 dice 100 times and recording how many times an 8 is thrown. Empirical, or also known as experimental probabilities, could estimate theoretical probabilities. Theoretical or formal probability involves probabilities derived from a theoretical space of outcomes. The definition of theoretical probability says that if all outcomes in a sample space are equally likely, then the probability an event theta will occur is defined as follows. P of theta is equal to the number of outcomes in theta, your desired result, out of the number of total possible outcomes in the sample space. The sample space, omega, can be presented as an area model using shapes, like this Venn diagram that you see. The theoretical probability of rolling an 8 could be found by looking at the sample space, all possible outcomes, and dividing the number of times an 8 could be rolled by the total number of outcomes. If I roll 2 dice, all possible rolls can be shown in this chart. The amount of times that 8 can be thrown would be if the first die is a 6 and the second is a 2, if the first die rolls a 5 and the second a 3, or if both dice are 4s, or if the first die is a 3 and the second is a 5, or the first die is a 2 and the second is a 6. There are 5 different possibilities for 8 to be thrown. So the number of desired possibilities is 5. 5 times you could get an 8. And the denominator of that fraction for our probability is the total number of outcomes in the sample space. So how many options here? 6 times 6, so 36. The theoretical probability of actually rolling an 8 is 5 out of 36. So maybe Aurelie shouldn't bet her money on the 8. A probability space is a model of a random experiment that consists of, number 1, a sample space, omega. This Greek letter omega will represent the sample space, meaning the set of all possible outcomes. Events would be subsets or collections of outcomes within omega. Like rolling an 8 is a subset of the possible outcomes when you roll 2 dice. Probability measure P is a function that assigns legitimate probabilities to events. The likelihood of a random event can be quantified. The empty set is the set of no elements, denoted by a 0 with a slash. An event theta that cannot occur is said to have no outcomes in the probability space such that theta is the empty set, which suggests that the probability of theta happening would be 0 because there's no outcome inside of theta. That would be like, what's the probability of rolling 2 dice and getting a 15? You can't get a 15. So that would be an empty set, and the probability of rolling a 15 would be 0. Remember, P parentheses theta is pronounced P of theta. We're using probability as a function. The axioms of probability define a random event. Theta is a part of the set of omega. This curly E is pronounced is a member of. So we would say theta is a member of omega. Basically, theta is in omega. Then the probability of event theta, denoted as P of theta, P parentheses theta, must satisfy the following axioms. Number 1, P of theta must be between 0 and 1 inclusive. If the probability of an event happening is 1, that's 100%. And if it's 0, that would be 0. The probability of omega is 1. So the probability of getting anything that's in the entire set would be 100%. And our third axiom is specifically for disjoint events. When the intersection of theta 1 and theta 2 is the empty set, meaning there's nothing in common between two separate events, then the probability of the union of those events would equal the probability of the first event added to the probability of the second event. An even more formal way of writing that would be with this big U and this summation. For example, theta 1 represents the students who prefer math, theta 2 represents students who prefer science, and omega represents the entire sample space. We will come back to this Venn diagram as we explain probability elementary rules. Intersection. The symbol for intersection is this upside down U. It's pronounced and. Some people see it as like an A without the line through it, and that's how they remember that the upside down U is the symbol for and. The intersection of two events, denoted as theta 1 intersection theta 2, or pronounced theta 1 and theta 2, consists of all outcomes that are strictly shared by the events. Typically, the intersection of events can be identified by this and that phrasing. For example, what is theta 1 intersection theta 2? The intersection would only look at the students that prefer math and science equally, Samil and Sarthik. If they were asking for the probability of the intersection, that would be 2 students out of a total of 10 students. So 2 out of 10 or 1 over 5. The union of two events, the symbol for union is a big U, and it's pronounced or, denoted as theta 1 union theta 2, consists of the outcomes across all combinations of the events. That is, the outcomes in theta 1, the outcomes in theta 2, and the outcomes in the intersection of theta 1 and theta 2. Alternatively, an outcome is in theta 1 union theta 2 if it is in at least one of the events theta. And typically, the union of events can be identified by either or phrasing. The students in the union of events would be students who prefer math or science. That would be all 10 students. For mutually exclusive or disjoint events, two events, theta 1 and theta 2, are said to be mutually exclusive or disjoint if they cannot occur at the same time. That is, theta 1 intersection theta 2 is the empty set. That means the probability of this intersection is 0 because there is no intersection. The intersection is empty. For example, theta 1 could represent getting an odd number after rolling dice, and theta 2 could represent getting an even number while rolling the dice. In this case, there are no numbers that are both even and odd, so these are mutually exclusive or disjoint events. The set difference of two events uses this / symbol. It can be pronounced set difference or relative complement. The set difference of two events, denoted by theta 1 set difference theta 2, removes the outcomes from theta 1 that are shared with theta 2. Particularly, only the outcomes that are only in theta 1 are considered. The probability of set difference of theta 1 and theta 2 is equal to the probability of all the outcomes in theta 1 minus the probability of the outcomes that are shared by theta 1 and theta 2, also known as the intersection. Or the probability of the set difference of theta 1 and theta 2 is equal to the probability of theta 1 intersection theta 2 complement. Typically, the set difference of two events can be identified by this but not that phrasing. If I'm asking for the probability of theta 1 set difference theta 2, I'm asking for how many people are in theta 1 but not in theta 2. That would be Siddhi, Om, Kason, Cameron, and Kiana. We would not include Samil and Sarthik because they are also in theta 2. So this but not that. Complement of an event. The complement of an event theta, denoted by theta to the power of c, pronounced theta complement, consists of the outcomes not in theta. Think in binary. An outcome is either in theta or it's not in theta, meaning it's in theta complement. Consequently, theta and theta complement are disjoint. There's no overlap here. Practically, it may be easier to compute the complement of an event than the event itself. For example, the probability of theta complement is equal to the probability of omega minus the probability of theta, meaning the probability of an outcome not in theta would equal the probability of all possible outcomes minus the probability the outcome is in theta. We already know that the probability of all possible outcomes is 1, the decimal version for 100%. So the probability of theta complement is equal to 1 minus the probability of theta. For example 1, a consumer magazine conducted a survey of a random sample of US adults about what credit cards they carry. The result of the survey suggests that 74% have a Visa credit card, 26% have an American Express credit card, and that 12% have both credit cards. Diagram the probability space for this problem. Let's let theta 1 equal Visa card owners and theta 2 will equal American Express card owners. The probability of theta 1 is 74% or 0.74. The probability of theta 2 is 0.26, and the probability that they have both cards, meaning the probability of the intersection, is 12%, 0.12. If the intersection is 0.12, the probability of theta 1 is 0.74, then the probability of someone owning a Visa card but not owning an American Express card would be 0.62. So that 0.62 plus 0.12 equals 0.74, the total probability of theta 1. The probability that someone only has an American Express card would be 0.14 because 0.12 plus 0.14 is 0.26. The probability of the whole sample space is equal to 1. So to find the probability that someone owns neither Visa nor Amex, we'll take 1 and subtract 0.62, 0.12, and 0.14. Which equals 0.12. Part B, what is the probability that a randomly selected adult will have either a Visa or Amex card? This is asking for the probability of the union of these two events. So 0.62 plus 0.12 plus 0.14, which equals 0.88. Part C, what is the probability that a randomly selected adult does not have a Visa card? This is asking for the probability of theta 1 complement, so not Visa. That formula is 1 minus the probability of theta 1, which is 0.74, and that equals 0.26. What is the probability that a randomly selected adult has a Visa card but not Amex? This is asking for set difference, the probability set difference between theta 1 and theta 2. And we already calculated that in our diagram, which is 0.62. What is the probability that a randomly selected adult has neither a Visa nor Amex card? We also already calculated that. This is asking for the probability of the union complement, so not in the union of events. 1 minus the union, 0.88, and that's 0.12. Number 2, in a freshman Calculus 2 class of 125 students, suppose that 72 have taken AP Calculus in high school, 54 took AP Stats, and 40 students took both courses. Diagram the probability space for this problem. Omega is equal to 125 total students. Let theta 1 equal students that took AP Calculus, and theta 2 will equal students that took AP Stats. If the intersection is 40, then the students that only took AP Cal and not Stats would be 32, because the total number of students that took AP Cal is 72. And the number of students that took AP Stats but not AP Cal would be 54 minus 40, so 14. To find the number of students that took neither of those courses, we'll take the total of 125 and subtract 32, 40, and 14. Which is 39 students. Part B, what is the probability that a randomly selected student in this class has taken both AP courses? This is asking for the probability of the intersection, which is 40 students out of the total 125, reduced to get 8 out of 25. Part C, what is the probability that a randomly selected student in this class has taken AP Stats but not AP Cal? This is asking for the probability of theta 2 set difference theta 1, which we already calculated as 14 students out of the 125 total. What is the probability that a randomly selected student in this class has not taken AP Stats? You could write this as probability of theta 2 complement, so the probability of selecting someone not in theta 2. The formula for that is 1 minus the probability of theta 2, so 1 minus 54 over 125, which is 71 over 125. Part E, what is the probability that a randomly selected student in this class took neither AP Calculus nor AP Statistics? We actually already calculated this, but this is basically asking for the union complement, which is 1 minus the probability of the union of these two events, which includes both set differences and the intersection. That's 1 minus 86 over 125, which is 39 over 125. What is the probability that a randomly selected student in this class took only one of the AP courses in high school? This would be asking for the probability of the union minus the probability of the intersection. Probability of the union of these two events was 86 over 125, and the intersection was 40 out of 125. Subtract, and that's equal to 46 over 125. You could have also calculated this by adding the two set differences, so 32 over 125 plus 14 over 125. And that's basic probability and set theory.